All right, so we are now going to talk about infrared spectroscopy. All right, so here's the fundamental principle. Organic molecules, specifically bonds in those organic molecules, can absorb infrared radiation. That causes these bonds to stretch and also bend. Different bonds will absorb radiation at different energy levels. Okay, so a CO bond will absorb infrared radiation at a specific energy. A CH bond, an sp2 carbon to an H, a C double bond O will all absorb infrared radiation at different energy levels. So what that really means is we can look at an IR spectrum of a molecule to then determine what specific bonds or really functional groups that molecule has as a way to help identify the molecule or really confirm its structure. All right, this is the fundamental principle of infrared spectroscopy. So let's look at a typical spectrum here, okay? So if we look at our y-axis, we have transmittance, right? That's the amount of light that goes through. So the top of the scale we have 100, at the bottom we have 0. So if we look at our first signal here, right, we have nearly 100% transmittance, okay? So light is going through our molecule. So what we're most interested is not looking at when we have 100% transmittance, but when we have 0 transmittance or when we have absorbance. Okay, so we're really looking at identifying peaks. Anytime we see peaks here, means that the molecule is absorbing very specific energy levels. All right, so we're looking at absorbance. All right. Our x-axis here is wave number, okay? So this is just basically a number that really corresponds to our energy, okay? It corresponds to our energy or our frequency. So here we're just using numbers that are easy for us to work with. Our general scale is from 4,000 wave numbers to about 500 wave numbers. And the official unit of a wave number is 1 over centimeters, all right, 1 over centimeters, okay? So you can see that unit here. But these are just values that help us to identify where these peaks come, all right, where these peaks are, okay? So this is what a typical spectrum looks like. We're looking for absorbance. We can see what that intensity is by how large the peak is, but most important, where these absorb, where these peaks actually absorb, okay? We'll be looking at these values here on what energy is absorbed, all right? To break this down and simplify it, what I'd like to do is really talk about 5 different zones. So we're going to be focusing on our attention on 5 zones. Zone 1, Zone 2, Zone 3, Zone 4, and Zone 5. These are the 5 zones that are going to be important where we can see peaks, okay? This last region here is called the fingerprint region, okay? And we're not really going to be focusing on this region that much because there's generally a lot of peaks here, and these peaks tend to overlap, okay? So there's a lot of peaks and they tend to overlap, so it's hard to identify a molecule looking at the fingerprint region when we're just learning basic infrared spectroscopy, all right? So what's important is going to be looking at our 5 zones, okay? And again, we're going to be looking at bonds, all right? So the first thing we have to do is we really have to look at our table here. This table is going to be very, very important to understanding IR, right? These are our characteristic IR stretching frequencies or energy, all right? So let's break this down into our 5 zones. So our first zone is zone 1. This comes between 3,700 and 3,200 wave numbers, right? 1 over centimeter is wave numbers. So there's three main functional groups we're going to be looking at. First is an OH bond, right? And that can be found in the functional group of an alcohol. So if your molecule has an OH bond, that means that it will absorb infrared radiation somewhere between 3,650 and 3,200 wave numbers. All right? So OH bonds will absorb between 3650 and 3200. And then here we can talk a little bit about the intensity. This absorbance is usually going to be broad. It's not going to generally be a sharp peak, and it's usually pretty strong. It says variable here, but generally those are pretty obvious and pretty strong. So that's the first bond we need to look at. The second bond we need to look at is an alkyne, but not the carbon-carbon triple bond. We're actually specifically looking at the sp carbon to H. So we're looking at an sp carbon to H bond, okay? And an sp carbon to H bond will absorb at about 3,300 wave numbers, and generally that's going to be quite strong. The last bond we need to look at is an NH bond that can be found in amides or amines. So an NH bond will absorb in this same zone, and that will absorb between 3,500 and 3,300 wave numbers. And again, those are often broad, okay? So in zone 1, there's three bonds we'll be looking for, an OH, sp carbon to H, and an NH, and they can come at the wave numbers shown here. All right. Next is zone 2. Zone 2 is from 3,200 to 2,700 wave numbers. Okay. There's really four groups we need to look at. First is an sp3C to H bond. That can come between 2960 and 2850. Right? That would be an alkane functional group. All right. Next is aryl or a vinyl. That's an sp2 carbon dihydrogen. That can come between 3,100 and 3,000 wave numbers. And you'll see both of these, the intensities can be variable. Sometimes these peaks are very intense, other times they can be small. All right. And to help distinguish these, I like to look at what I call the 3,000 line. So anytime I'm looking at a spectrum, I'll look at the mark for 3,000 and I'll draw a line straight up here, right? So if I see peaks to the left of this line, from 3,100 to 3,000, these are going to be my sp2 carbon dihydrogens. And if I see peaks to the right of the line from 3,000 to 2,850, right, these are going to be my sp3C to H's, right? And as you can imagine, in organic chemistry, we have a lot of sp3 carbon dihydrogens, so it's generally going to be rare for us not to see a peak there, all right? So that's what I like to call the 3,000 line. And as we're seeing spectra, you'll see me draw that in a lot. Next is an important peak, an aldehyde peak. This is the sp2C to H bond. So let's kind of draw that out here. So if you remember the aldehyde functional group, we're specifically looking at the sp2 carbon to hydrogen bond, right? We're looking at this bond right here. So that bond will have two peaks, one peak at 2,900, but you'll see that peak at 2,900 is generally going to be kind of hidden in our sp3C to H's. Okay, so the 2,900 peak is a little hard to see, but what isn't hard to see is that peak at 2,700. Okay, because nothing else absorbs at 2,700. So if you see a peak at 2,700, that's telling you that you have an aldehyde functional group, right? And the last bond or last functional group we need to look at is an OH. But this isn't any general OH. This is an OH of a carboxylic acid. Notice above here, an OH of an alcohol is always found in zone 1. But the OH of a carboxylic acid is found in zone 2. So if we draw out our carboxylic acid functional group here, this OH peak of a carboxylic acid, right, this bond here is found in zone 2, okay? So that's an important distinction. And that will be from 3,000 to 2,500, okay? So again, these are overlapping with some of these other peaks, but it's easy to identify the OH peaks is because they are very, very broad. The other peaks we see are generally going to be sharp. They'll be very distinct peaks. But that OH of the carboxylic acid, that's going to be a broad peak. All right? The next zone we're going to look at is zone 3. That comes between 2,300 and 2,100. And these are going to be our triple bonds. So my carbon-carbon triple bond or a carbon triple bond to an N. So a carbon-carbon triple bond is between 2260 and 2100. A carbon triple bond N is between 2260 and 2200. Okay? So our triple bonds are found in zone 3. No triple bond, no peak in zone 3. These both have variable lengths, but they are generally sharp. Okay? Our next zone is zone 4. That comes between 1950 and 1650. And you can see there's a lot of common things we have. Carbonyls, okay? Carbonyls can be found in lots of functional groups. Aldehydes have carbonyls, amides, ketones, carboxylic acids, esters, enones, conjugated systems. These are all going to be found in zone 4. I want you to notice all of these are going to be very, very strong peaks. It'll be obvious that you have a carbonyl. And in my class, and generally speaking here, we can just combine these, right? I don't need to separate these out to get specific because there's a lot of overlap. So generally speaking, if we see a peak from 1750 to about 1680, right? We know these enones can be a little less than that. A conjugated can be a little less. But generally speaking, a peak from 1750 to 1680 is going to be a carbonyl peak. All right? So all of these are carbonyls. There is one additional peaks we see, aromatic overtones. So if you have some aromatic compound, generally benzene rings, okay, you will see 3 or 4 small bumps, 3 or 4 small bumps between 1915 and 1750. All right, so those are just small little bumps. They're not strong. The last zone we need to look at is zone 5. That comes from 1680 to 1450. And these are going to be my double bonds. So a carbon-carbon double bond of an alkene or a carbon-carbon double bond of an aromatic compound. Alkenes are generally between 1680 and 1620. Aromatic compounds generally will have a peak at 1600 and then another peak between 1500 and 1450. All right? So aromatics generally will have 2 bands. And again, these peaks are generally going to be sharp, okay? And they can be of variable absorbance. So they can be short or long, small or large, but they will definitely be sharp. All right? So these are the main zones that we need to look at and know. What I want to do now is just show you examples of what these actually look like. So I have a lot of sample spectra here. And what you'll notice is in the bottom right corner, we have the actual structure, okay? So what we're going to do is basically analyze the spectrum or the structure to see if we can identify the peaks here, all right? So the first thing we see is if we look at this peak here, I can see a nice big peak that's at about 3,300. What does that correspond to? Well, if you go back and look at our table, right, a big peak around 3,300 is my SPC to H, okay? So we can identify this peak as an sp carbon to H bond. Remember, this is always a bond, all right? That's zone 1. I move into zone 2. I like to draw in my 3000 line. There's nothing to the left of this, but I do have a couple of peaks here, okay? And those are going to correspond to sp3C to H's. Any peak from around 3000 to 2850 corresponds to sp3C to H's. Next, we see a large peak here. That's at about 2100. That's where we have our triple bonds. So this is a C triple bond C, right? Or it could be a C triple bond N. But obviously here it's going to be a C triple bond C, all right? And then in my class, once we get kind of below 1450 or so, we can kind of ignore the rest of these peaks in the fingerprint region, right? So clearly what we can see here is we have an alkyne, and we have a terminal alkyne. Because I have this sp carbon to H, right, that's that bond here. I have a terminal alkyne, all right? Now, a couple questions for you. IR is very useful in determining what functional groups we have. So here we can clearly draw the conclusion that we have a terminal alkyne, okay? What we can't tell, though, is how many alkynes we have or how many sp3 carbons we have. It never tells us the amount, just that it's present, all right? So here we have 1, 2, 3, 4, 5, 6. This is one hexyne, right? What would the spectrum look like if we had octyne? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. What would our spectrum look like if we had one octyne? It would look exactly the same, okay? Our peaks don't tell us how many of the functional groups we have, how many atoms. It doesn't tell us how many carbon-hydrogen bonds we have, right? So if I extend this chain longer, I've already got CH bonds here and CH bonds. I can't tell the difference there, all right? But what if we had this structure here? What if instead of having one hexyne, we had two hexyne? 1, 2, 3, 4, 5, 6. So what if we had this structure? How would this IR spectrum change? Well, we'd still have our carbon-carbon triple bond. We'd still have our sp3C to H's, but this is no longer a terminal alkyne, right? This is a methyl group, a carbon. We don't have an sp-C to H bond. So 2 hexyne would not have this peak here. This peak would be gone. It would just be a straight line across. All right? Let's continue on. Let's look at our next structure here. Here we have an alkene, right? So let's analyze our structure, our spectrum. Nothing in zone 1. I get to zone 2, right? I like to draw in my 3000 line. So here I can see I have a peak at about 3100, right? Again, we always want to go back, refer to our table. What do I have when I have something to the left of my 3000 line, right? This is going to be an sp2 carbon to H bond, right? And I'm representing a bond. I always have to draw two atoms, right? It's an sp2 carbon to H. I have a bunch of peaks to the right of that between 3000 and 2850. These correspond to sp3C to H bonds, okay? As I come across, sometimes you'll see small peaks, right? This is a small peak. We're basically going to ignore it. But there is a large peak here. That's at about, let's say, 1620 or so, right? 1630. What does that correspond to? That is in our zone. That is in our zone 5 here, right? And that corresponds to a carbon-carbon double bond. All right. So clearly, what we can see here, right, is we have some sort of alkene. We have an alkene. all right? And that makes sense with this structure here. Now, again, from the IR, we can't tell what alkene we have. So this same spectrum could fit this molecule here. It could fit this molecule here, right? So we have to be aware that it's not going to tell us how many we have. You could have two alkenes. The spectrum is going to look very, very similar. So in understanding the basics of IR spectroscopy, right, we really need to understand that it doesn't tell us how many of those functional groups we have, just that we have them. Again, let's do another thought experiment. What if I had this structure here? What if I had this alkene? How would the spectrum change, right? We'd still have our carbon double bond. We'd still have sp3c to H's. But what we should notice here, right, is here we have methyls. This is a tetra-substituted alkene, which means there are no sp2c to H's. So the IR spectrum of this alkene that's tetra-substituted will look very similar, but that peak would be gone. We wouldn't see that peak. All right? Looking at our next structure here, right, in zone 1, now we see a big, broad peak here in zone 1. So that's clearly going to be an OH, right, or an NH, okay? And we'll see NHs a little later, but when you have a nice, big, broad peak here, that's always going to be an OH of an alcohol. We get to zone 2, we draw our 3000 line, nothing to the left of it, a bunch of peaks between 3000 and 2850. We're generally always going to see these. These are sp3 carbon to hydrogen bonds. Nothing in zone 3, nothing in zone 4. Once we get to our fingerprint region, we can generally ignore that. So what does this tell us, right? This tells us that we have an alcohol. Okay, we have an alcohol here. And we can see that functional group in the structure. Again, this alcohol could be lots of things. It could be propanol, right? It could be cyclohexanol. There's a lot of different molecules that can have a very similar IR spectrum. Okay, next we'll start looking at some carbonyl peaks. So when we do our analysis here, we have nothing in zone 1. We get to zone 2, we draw our 3000 line. We have a few peaks here. These are sp3c to H's. Nothing in zone 3. We get to zone 4 here. Now we have a really large peak in zone 4. That is our carbonyl. That is our carbonyl at 1718. All right. Once we get to our fingerprint region, we can kind of ignore this. So in this molecule, we know we have a carbonyl. All right. And this turns out to be a ketone. All right. One thing to notice, right, with this table, if you look at our ketones, they're 1750 to 1705, right? Generally the same as an ester, so it's hard to tell the difference between an ester and a ketone at this basic level, but there's other ways to determine those differences, okay? All right, so that's what a ketone looks like. Next, we have a functional group here. We have an aldehyde. Here we can definitely distinguish this. As we go through zone 1, tiny peak we ignore. We look at zone 2. I draw my 3000 line. I circle my peaks from 2850 to 3000. Those correspond to sp3c to H's. And now I have this other peak way out by itself at about 2700. What is that? There is only one peak that absorbs at 2700. And what is it? 2700 is my aldehyde, okay? So this peak here at 2700, this is our aldehyde, but specifically it is this bond here. It's the C to H bond, all right? Okay. Now, when you draw an aldehyde, what else does an aldehyde have? It has a carbonyl. Where does that show up? Right? Nothing in zone 3, but in zone 4, we've got a huge peak at 1718. That is the carbonyl of the aldehyde. So you see, when you have an aldehyde, you have two distinctive peaks. You've got your 2700, your sp2C to H, and then you have the C double bond O at 1718. Okay, we get down to the fingerprint region, we can basically ignore that. This peak here is important because it tells us we have an aldehyde. Again, and we don't know how many carbons we have here. We definitely have some because we have sp3 carbons, but we don't know exactly how many. Again, the purpose of IR is to tell us, do we have that functional group or not? All right. Next example here, we have in enone, we have a conjugated ketone. Okay, so we have a conjugated alkene and ketone. We get into zone 1, nothing here. Zone 2, now we do have some peaks, right? So if I draw in my 3000 line here, right, we can clearly see we have some peaks to the left and the right. They are small, right, but they are there. So these correspond to our sp2C to H's between 3000 and 3100, and the sp3C to H's between 3000 and 2850. Nothing in zone 3, right? And now we get into our zone 4. All right, what we can see here is we have a big bunch of peaks here at 1686. That's still in zone 4. That is our carbonyl, right? Because this is kind of low, it tells us that we most likely have a conjugated system. And then here we see our peak at about 1600. That's our C double bond C, okay? So generally in my class, what I'm going to do is anytime I give you a carbonyl, right, I'm generally going to give you carbonyls that don't overlap into zone 5. So my carbonyls peaks here, I'm going to give you things that I'm not going to go all the way down to 1665, right? It'll be closer to 1685. It'll be above 1680. So you can clearly see that that carbonyl peak is in zone 4. And if you look at that peak here, that's clearly in zone 4, not in zone 5. All right? Next spectrum here, nothing in zone 1, right? We draw on our 3000 line. A few peaks to the right of it. Again, those are sp3C to H's. Nothing in zone 3. Zone 4, we have a huge peak here. That is our carbonyl, 1740. We can basically ignore our fingerprint region here. Again, here, this is an ester, okay? And what we talked about here, esters and ketones are quite similar, so I'm going to have to give you some extra information to determine whether you have an ester or a ketone, right? But what you'll notice with an ester is you generally have 2 O's, right? You have 2 O's. The ketone might just have 1. All right, our next example we'll see is a carboxylic acid. These have very distinct peaks. So if I look in zone 1, I don't have anything separate in zone 1, right? But if I draw my 3000 line, I can clearly see some peaks to the right of that. That's my sp3C to H. But in the background here, I can see this big, broad peak. And that big, broad peak here is in zone 2, right? So when we have this big, broad peak here, and it's in zone 2, that is the OH of a carboxylic acid. Okay, that's the OH. So when you have this big, broad peak in zone 2, that tells you you have your OH of a carboxylic acid. Let's review and look at what an alcohol looks like. Remember, the OH of an alcohol was clearly in zone 1. Okay, so alcohols are clearly in zone 1. Carboxylic acids really expand all the way out through zone 2, and that's how you can tell you have a carboxylic acid. Nothing in zone 3. We get to zone 4. Of course, we have that large carbonyl peak. So this is the carbonyl peak of the carboxylic acid. Carboxylic acid is going to have these two big peaks, the OH in zone 2 and your carbonyl. Okay, we can ignore everything below 1500, and clearly we have a carboxylic acid. All right. The next spectrum that we can look at here, and I think this is the last one we're going to look at. Let's identify this. Nothing in zone 1, right? Zone 2, we can draw in our 3000 line. We see we have some peaks to the left of that, between 3100 and 3000. Those are clearly sp2 C to H bonds. We have peaks to the right of that. Those are sp3 C to H's. Nothing in zone 3. In zone 4, we see 3 or 4 small bumps, right? Those are what our aromatic overtones look like. That's a really good indicator, of course, that you have an aromatic ring, all right? And then our last peak, we can see we have a peak here, right? And that's our C double bond C of our double bond, right? And there's generally a second one of those, all right? And we can kind of ignore everything below 1450. Clearly here we know we have an aromatic ring of some kind. We have a benzene ring, right? And because we have some sp3 C to H's, we have to have some sort of alkyl group coming off that, all right? So that is basically kind of an introduction to infrared spectroscopy. It's important that you know the table, right? So it's important for us to know this table, analyze this by the basic zones, right? And then we saw examples of the key functional groups we need to look at.